Hi guys, I'm Smiley here. We're now going to look at the log laws. This is exercise 5D from your essentials text. So what they want us to do is to simplify 2 log base 10 3 plus log base 10 16 minus 2 log base 10 6/5. It looks pretty complicated, but it's not too bad. What we want to do for a start is put it so that we don't have anything in front of the log base 10. So, for example, for 2 log base 10 3, let's change that to log 10 base 3 to the power of 2. Log 10 16 stays the same, and then negative 2 log 10 6/5, we take the 2 as well and put it squared. So we get log 10 6/5 to the power of 2. There we go. Now we have gotten rid of those 2's out the front. Now I'm going to square those numbers, so we get log base 10 9 plus log base 10 16 minus log base 10 36 on 25. In order to add and subtract these, what I need to do is to multiply. So I get log base 10, they've all got the same base now, so they've all got log 10 there, so I can add and subtract them. 9 times 16 is equivalent to 9 plus 16, and to subtract 36 on 25, I actually multiply by the inverse of that, or 25 over 36. There it shows it there. And that gives me log base 10 2. Let's look at another one. Here we want to solve for x. Log base 2x equals 5. What that means is that we take the x and we put it on the left, and then we put 2, which is our base for the log, to the power of 5. So x will equal 32. Log e 3x plus 1, the same deal. We do e to the power of 0, and that equals 3x plus 1. So in order to get rid of the log, we take the base of the log and we put it on the right with the number there to the power. So 3x plus 1 equals e to the power of 0. Anything to the power of 0 is 1. So then we can just solve for x. 3x equals 0 and x still equals 0. Log base 2, 2x minus 1 equals 4. Let's look at that. Take the 2, put it to the power of 4. We can then get rid of the log, and we've got 2x minus 1 equals 16. 2x equals 17, and x equals 17 over 2. Moving on. Let's do some more of those. So log x 27 equals 3 halves. So take the x out, put it to the power of 3 halves, and that equals 27. So therefore x is going to equal 9. Log e, 3x plus 1 equals 0. So we get 3x plus 1 equals e to the power of 0, or 1. 3x equals 0 and x equals 0. How about this one here? This is a little bit more tricky. We've got log e x minus 1 plus log e x plus 2 equals log e 6x minus 8. In order to add the 2 logs on the left, we multiply them. So x minus 1, x plus 2 equals log e 6x minus 8. We can then expand by FOIL, if you like, and we get x squared plus x minus 2 equals 6x minus 8. Notice, because the logs are the same, I can now, I can get rid of them once I've added the log e x minus 1 and log e x plus 2. Solve in the usual way. We get x squared minus 5x plus 6 equals 0. I use cross multiplication to do that, and I find that x is 3 or x is 2. Now they want us to sketch some graphs. So let's sketch the graph of y equals 3 log 2 2x. So here is the basic graph of y equals log ex. And note that I've got a intercept at 1, 0, and then I put a point in of e and 1. So I've just substituted in e for x, and anything where you've got log e, or log 10, 10, log 2, 2, we're going to end up with an answer of 1 there. So it's a handy point to put in. Let's think about what happens in this graph. So from the basic graph of y equals log ex, we're going to dilate by a factor of 3 from the x-axis. We're also going to dilate by a factor of half from the y-axis. So there's 2 dilations there. So our mapping is xy becomes half x and 3y. Remember that a dilation from x-axis affects your y value. That's why we get a 3y there. And a dilation from the y-axis affects your x values. That's why we get half x. So with those points there, we've got 1, 0 becomes half 0. Because if x is 1 and then it's got to become half x, 1 becomes half. 0 stays the same because even though we multiply 0 by 3, that's still 0. E and 1, that point, becomes half e and 3 for the same reasons. And there's the graph there. I've got my intercept still there, and then I've got my point, which was 1, 0, which was E1. That's half e and 3. I marked that in as well. Notice that I still have the intercept. Let's try this one here. We've got y equals log 2, x minus 5 plus 1. You already can probably sort of think what sort of transformations that would be talking about there. We've got 5 units in the positive direction of x and 1 unit in the positive direction of y. Let's see what happens there. Here we have our basic log graph of, log 2x graph, and again we've got the point 1, 0 marked in, so that's the intercept, and then I put in a point 2, and I know that log 2, 2 is going to equal 1. They're easy points to put in. Let's do the mapping then. xy becomes x plus 5 and y plus 1. Let's change the points. So 1, 0, let's map that with the new thing of plus 5 and plus 1. We get 6 because 1 plus 5 is 6, and we get 1 because 0 plus 1 is 1. How about the point 2, 1? 2 plus 5 equals 7 and 1 plus 1 equals 2. Let's put that on. There it is there. And our asymptote there is x equals 5. Notice I can see that because I've got x minus 5 in the equation, meaning that my new asymptote is x equals 5. I have not marked in the point of the intercept, the x-intercept. I should have done that, and that's something you should write in as one of your points. Keep that in mind. Let's try this one. Y equals negative log 3, x plus 4. So here's the basic graph of y equals log 3x. So again, I've got the point 1, 0, and then that different point of 3, 1. Remember, log 3, 3 will equal 1. This is a translation of 4 units in the negative direction of x and a reflection in the x-axis. So the negative direction of x maps x to x minus 4, and then the reflection in the x-axis will affect the y values, so we get negative y. 1, 0 becomes negative 3, 0, so that still stays as an x-intercept, and 3, 1 becomes negative 1, because 3 minus 4 is negative 1, and 1 made into negative y becomes negative 1. There it is there. So now we have our asymptote at x equals negative 4. Look at that. We can always see that because it's the thing in the brackets next to the x there. There are the points marked in, and we do see the x-intercept there. That's important. The y-intercept, it would also be important to mark in. So also find that by solving for y when x is 0. Let's sketch y equals 2 log e x plus 5 minus 3. You can start to think about what the translations will be then, how the graph might look. Here's our basic graph of log ex. Don't be afraid by the e, it just means that we have a point of e and 1, and then as usual a normal point of 1, 0. With translation 5 units in the negative direction of x, with dilation by a factor of 2 from the x-axis, and we have a translation 3 units in the negative direction of y. So let's put our mapping there. xy becomes x minus 5. That's the translation 5 units in the negative direction of x. And 2y minus 3. The 2y being our dilation, a factor 2 from the x-axis, and negative 3 being our translation 3 units in the negative direction of y. 1, 0 becomes negative 4, negative 3, because 1 minus 5 is negative 4. 0 times 2 minus 3 is minus 3. E1 becomes E minus 5 because E minus 5 is E minus 5. And 1 times 2 minus 3 is minus 1. And here's our new graph here. We have our point of E minus 5 and minus 1. We have negative 4 and negative 3. Notice I've also marked in the intercept here, and that's important. I forgot to do that in the previous two. Don't forget that. So when x is 0, y just equals 2 log E5 minus 3. And when y is 0, we get e to the power of 3 halves minus 5. And that's all we need to do for exercise 3D.